afternoon, everyone. I'm afraid I'm battling uh, with my screen sharing. My computer's been upgraded and it's self-upgraded, and everything is now different, which doesn't help. But I see that our speaker is in the audience, and you have been watching some of the screen sharing where this is our monthly webinar, which we share with RSSAf. And in our monthly webinar, we try and get a topical speaker that's going to have an interest to most of the people. And we choose very good speakers, and they not only entertain us, but they help educate us as well and give us some really good ideas and show us what's going on. We've got some new members, and I'm sorry, the way this is now showing, I can't read them, but that has been coming up. And we've got some future talks coming up as well. These are the ones that we know about, and all the time we're arranging them. Right. I'm going to say something a little bit about our speaker today, and it's Professor Michael Bodunrin. He is a colleague at Wits University with me. So he's in the School of Chemical and Metallurgical Engineering at the University of Witwatersrand. And his work spans biomedical and energy material with a focus on societal impact. Key focus of his research is the development of titanium alloys with low density stainless steels for biomedical implant applications. Sorry. With particular emphasis on understanding and improving their corrosion performance in physiological environments. He's also actively involved in research on complex concentrated alloys for hydrogen storage. He's a Y1 rated researcher with the National Research Foundation of South Africa, and he is a recipient of the ICANICS Young Scientist Award in July 2024. As well as that, he's a chartered engineer, a CEng, with the Engineering Council of UK, and a member of what we call IOM3, which is the Institute of Materials, Minerals and Mining, that's based in the UK. And I know his work fairly well, so he's going to give us a very good talk. Right, so what I'm going to try and do is try and kill this, and then he can bring up his presentation and we can start the talk. So welcome, Professor Bodunrin.
Thank you so much, Prof. Cornish. Screen. Okay.
Coming.
Yeah, are you able to see my screen?
It's coming. Yes, now I am.
Okay, good.
Right,
okay. All right. All right. Thank you so much for the wonderful introduction. Today, I would like to chat to you about the topic closing the longevity gap by using affordable metallic bioimplant materials. When I was approached to give this talk, I wasn't sure whether I should focus on materials for energy, which is funded by the Royal Society in the UK, or focus on materials for health, which is something I've been doing for many, many years. But I asked myself a question. If I were to give this talk in person and I had to travel to Cape Town and I accidentally find myself on the plane, and I had to sit with someone or sit beside someone who is a member of the Royal Society of South Africa. Who would that person be? And what kind of conversation would I have for the person? I think that person would be no other person than Professor Abdul Karim. Um, and I think because of the work and his contribution in the public health space, it's only natural that a talk around materials for health would be quite reasonable. And it is for this reason why I chose this particular topic today. And I hope that as you listen to me, you would understand that this is more or less a conversation that I had imagined in my head that would happen between myself and Professor Karim if we were to travel from Johannesburg to Cape Town together on a plane. So please sit back and enjoy. I don't know if I will be able to entertain you, but of course, I believe that. So please sorry about that. I think it's one of the students. Um, in the corridors. So I believe that I believe that I'll be able to at least add a few things to your knowledge, or at least maybe give you some insight about some of the work we've been doing since 2014. But before I proceed, I would like to um, appreciate Professor Cornish for giving me the opportunity to engage this particular audience. She's the president of the Royal Society of South Africa. But before she became the president, she was more or less like a mother to me. Without her, I wouldn't have come to South Africa in the first place. Uh, I wouldn't have opportunity to do my PhD at WITS. And she's played so many roles in my career to date, and I can't even thank her enough. So if I should start now, I won't end until my entire time is up. But thank you so much, Professor Cornish, for having me. And I thank the Royal Society of South Africa for also having me. And of course, the Academy of Science of South Africa. So I don't work alone. Over the years on this topic, I've worked with so many collaborators, including my supervisors. Um, and I've also worked with students. There are students who have also worked on the same projects. So I can't even fit every one of them on the screen. So if you are my student and you've joined, please, and you've worked on this, please, if you're not here, forgive me. It's just impossible to fit every one of you here. So special thanks to my PhD supervisor, Professor Leslie Chown, and of course, Professor Yaya Shinara, who has also helped in recent times on the project. So I would also like to say thank you to late Professor Josiah, who was my co-supervisor. He died in 2024, but without their support, I wouldn't have started this project and I wouldn't have gone this far on this particular topic. So now to the main conversation. I would imagine what would be the first question that Professor Karim would have asked me. It would be, what do you mean by longevity gap and why should we bother about it? And I have a response to that. So advances in science and technology, or mostly medical science, have really given us the opportunity to live longer. And it has been estimated by 2050, the world population, the population of people who are above 60 years old will reach 2.1 billion. Of those people, 1.7 billion would be staying in developing countries. And we all know what our status is in Africa. So I don't think we have any developed country in Africa. So which means we'll have a lot of older people living in Africa. And when you're old, there are risks associated with it, especially if we look at the human bone. So the strongest bone in the body would be our hip bone. And as you age, you could have reduced bone density, which you could also have a situation where your bone becomes brittle, stiffness in joints, and all of these could lead to hip fracture. And as I grow older and interact more with people, um, I'm even convinced the more to continue working in this area because I know people I see every day who's got one or two members of their family facing the problem of hip fracture, especially older women. And I think we need to find a solution to this. It's not like the solution is not there. It is there actually, because we can treat it. But the major problem is the cost of treating it. So imagine what will happen in 2050 when you have more people living, more older people living in Africa, and they are not able to access treatment because of the cost of the implants. It's not only implant, there are other medical devices that has to just be made cheaper so that people can access treatment at an affordable cost. So, but as a metallurgist, implant would naturally speak to me because that I can contribute something. So I want you to have this cost, which is a ballpark figure at the back of your mind. That would be a typical cost of titanium implant, and it varies across the world. So if you go to India and Belgium, I think it's much cheaper than if you go to the United States. And of course, it also depends on whether you have medical aid or not. So all of these factors contribute to the cost. But even if you look at the lower aspect of the cost, which is about 1,500, you would see that that is pretty much expensive for most people living on this continent to be able to afford it. So, how can we solve this problem? It's a question that we've been trying to answer um, over the years. So, again, I've been tracking the burden of disease globally for some time now, using this particular website here, Our World in Data. And you would see that Africa seems to be the destination where, the burden of disease is higher. So we have poverty and we have high burden of disease. So how do we then make our lives better? And this is also reflected in a data that I would just show you today. So if you look at, I try to track life expectancy at birth and healthy life expectancy in different regions of the world. In Africa, when you're giving birth to, you expect to spend 64 years before, death. But of those 64 years, you can only live healthy for 56 years. And if you compare this to other parts of the world, the disease burden is really having effect on this particular data that we see here. So to reduce disease burden, we have to have access to affordable medical care. And that's basically what SDG 3 is all about, good health and general well-being. But Africa alone doesn't face this challenge. If we take the difference between life expectancy at birth and that of healthy life expectancy at birth, you would see that if we're in Africa, even though we're not living longer as expected when compared to people from America, Europe, and of course, maybe Southeast Asia. But the difference is not that much. So if you're in Africa, you are expected to suffer for 8 years due to one disease burden or one type of disease or the other. Then if you're in America, it's about 11 years, Europe, it's about 10 years. So how can we reduce the gap between life expectancy at birth and of course, healthy life expectancy at birth? This is the gap that we're trying to reduce. Can we make our older adults healthier? I would tell a personal story here. My father would be turning 73 in March. And so he has actually beaten this prediction, 64 years. But when he turned 69, he suffered stroke. And since then, he has remained dependent. He can't do anything on his own, despite all the medical intervention. How can we reduce this? As a metallurgist, what I could do would be to develop alloys that could help because I love metals. I love working on metals. And so maybe it's not a problem of stroke this time. It's a problem of hip fracture. How can I make implants cheaper? And And some of the efforts we've made over the years, I will be showing you in this presentation. So at least now, I think the gap is clear. It's what is predicted for you to have when you are giving birth to, and the amount of LT that you have there. Can we not have the difference between those variable, or parameters, LE and HLE? Can we not reduce it to 1 or 2, or if possible, 0? And this is the gap we're trying to close, basically. So, Prof. Karim asked, how do we close this gap? Well, I have some response or I have an answer to that as well. So, as a metallurgist who is looking at finding cheaper materials for or affordable medical implants, there are two ways to go about it, because the two common materials used for making bioimplant metallic bioimplants. One, we have titanium, and the other one is 316L stainless steel. Okay, with titanium, the major issue is that it is expensive. Well, yeah, steel is way cheaper, but it is highly dense. So we make implants for them, from them. It's the cheaper option, but because it's heavy, it would lead to another problem called stress shielding effect. So by the time you give the treatment to the patient, and they're wearing this implant in the body, instead of the bone to carry the load and get stronger, this load then is transferred to the stainless steel implant, and then you get a situation whereby even your bone becomes weaker. So the if you can make titanium cheaper, then you must find a way to make steel lighter, and that's what we have been trying in our research group. And this for me are more or less the two pathways that one could explore. But have we been able to make titanium cheaper? A little bit, but there's still a long way to go. And at the end of this talk, I'll be calling on fellow scientists to explore other pathways that I think are relevant. So we have these two major challenge. How do we reduce the weight or density of stainless steel, or how do we make titanium cheaper? So, Prof. Karim asked another question. Beyond the social and health benefits, like if we manage to if we manage to close the gap, it means we have healthier people in the society. Global burden of disease will reduce significantly. But again, what other opportunities would this create, especially within the African South African context? And I think this is very important. And I have a response to that as well. So we know that Africa is really wealthy when it comes to our mineral resources. And how do we convert our mineral resources to medical innovation? I think it's an opportunity for us as a continent. And I remember when I came in 2014, I started my PhD. One of the reasons why I wanted to really work on titanium was at that point, the South African government was really keen in establishing a robust titanium industry in the country. But I don't know what happened along the line. I don't think that is really a priority anymore. But if we look at what is coming in future, I think we can tap into this opportunity of exploring, adding more value to titanium, making it cheaper for bioimplant application. And I believe that it is a profitable venture. So the first idea it would be to look at titanium, which South Africa remains one of the largest producer of its ore globally. And I know that Kenya is also in that story, following recent data. Also, in terms, if you're trying to reduce the weight of stainless steel, basically, you have to, if you're trying to make stainless steel lighter, you have to then consider alloying elements like manganese and aluminum. I wouldn't have enough time to really tell you about some of the work we've done here, but I believe that maybe this is not the only opportunity I would have to engage this audience. So another time I can tell you what we've done in this area within the last 5 years. But I've done quite a bit with my colleagues over the last 10 to 12 years on titanium alloys. So, but if we look, there's this identity that we've got. Uh, Manganese, South Africa is the largest producer of manganese in the world. Gabon is the third largest producer of manganese in the world. But we also have iron ore in South Africa. We also have chromium ore in South Africa. So if we add value to these metallic minerals, we can create medical innovations that would be beneficial. And I want us not to forget the success story of 3Cr12 alloy. It's a metallic material that originated from South Africa and it's now being used globally. Since that alloy, I'm not sure we've created any other one that seem to be commercially viable. So this is a call on all metallurgists, chemists, or scientists to try and see how we can repeat the same success story of 3Cr12. Maybe this would happen in terms of lightweight stainless steel, or maybe it would happen in terms of titanium alloys. I mean, I think the future would tell, but we have a lot of work to do. So it's not only about adding value to our mineral resources in South Africa or generally in Africa. It's also for investors to see that this is a viable business. If you look at the bioimplant market over the years, it keeps, it keeps expanding. So the return on investment is guaranteed. If we can have unique alloys peculiar to South Africa or Africa, and we can compete in terms of price and performance of the alloys, then it means that we stand a chance to make some money while we're saving lives. So for investors who are on the call, I think this is something that we have to really think about. So those are the other benefits associated with, exploring affordable bioimplant metallic materials in Africa. So, like I said, I couldn't talk about the two ideas, so I'm going to focus on titanium today. And Prof. Karim would want to know, okay, what have you done in this area over the past years? And this is what I would begin to tell you. So the first thing we looked at is how do we reduce the cost of titanium? We need to first understand what are the factors that contribute to the cost of titanium. So the first one is that it's difficult to extract from its ore. The most reliable process that we've been using is scroll process, and that process is quite expensive. We need to find alternative way. In fact, if we are able to do that, I think we can reduce the cost of titanium and its alloys significantly. I think this was one of the things. This was one of the projects that was being carried out at CSIR around 2013, 2014. I did visit the pilot plant as at then, but for some reason, I don't think that is active anymore. And it's quite sad. So, but as a physical metallurgist, we could look at the expensive alloying elements that are added to titanium to make it perform its function and see if we can carry out some manipulations there and lower the cost. We could also look at how to optimize the thermomechanical processing pathways for developing different components from titanium. Of course, this also extends to optimizing machining parameters. So today I would share more on the expensive alloying elements and how we manage to play around that. And of course, I will also talk about the thermomechanical processing steps. So the pie chart that you see here just gives you what the contribution of each processing block is to the total cost of titanium metal or titanium alloys when you make components from them. So what we did was to look at the most utilized titanium in the world, which is Ti64. And of course, it's used in aerospace and it's also used in the biomedical industry. So vanadium it's very expensive. It's much more expensive than titanium. And as a result, we have to find a way to look at other elements that can fulfill the same function of vanadium and then see if we replace either fully or partially, it could have some effect on cost. And if we manage to reduce the cost, what effect would that have on the performance of the alloys. So if we look at Ti64, many people or previous researchers have tried to substitute 4 weight percent of vanadium with 4 weight percent of iron. The major problem is that you would form this phase. Now I'm going a bit into physical metallurgy, and this is the domain of Professor Cornish, actually, phase diagram. So if you had iron to titanium, the equilibrium phases you would have is what we call alpha titanium, which is the stable phase of pure titanium with an hexagonal close packed crystal structure. And of course, you also have the TIFE intermetallic compound. And when you have this TIFE intermetallic compound, that have negative effects on the mechanical performance or mechanical properties of the alloy. It's too hard, very brittle, it's not ductile. And if you use that in service, for example, as an implant, it could fracture in a brittle mode, and that could really endanger the life of people. The same thing would happen if you had to use it maybe for maybe aerospace applications. So even though efforts have been made to replace vanadium with iron, it turned out that it's not an entirely good idea, except if you can limit the amount of iron to about maybe 1.5%, according to some of the work previously published in this space. But that doesn't really give you the type of properties that you would desire when making, for example, components that would be put in human bodies. So with vanadium, you don't have this problem of intermetallic phase. So our idea is rather than doing what everyone has done, let's have partial substitution of vanadium with iron. So if we go back, you would see that the compositions that we've explored mostly here have partial replacement of vanadium with iron. And what we realized is that we were able to actually suppress the formation of this TIFE by retaining some vanadium in that composition. And the reason for that is vanadium diffusion is quite slower compared to that of iron in titanium. And then that can mitigate the evolution of TIFE intermetallic compounds. So we had that theory at the back of our mind that with the partial substitution, we should be able to suppress the formation of that TIF intermetallic compounds, but we don't know how that will influence the mechanical properties. Would we be able to produce the alloy in the first place? Thanks to Mintech and thanks to Pierre Rousseau at CSIR, we started with button samples of about 10 grams. Then we increased it to about 50 grams. When we had more fundings, we were able to produce 5 kg of this alloy. And these are pictorial evidence of the some of the processes that we took when we were trying to produce this alloy. So we were able to make the alloys, and this is what the 5 kg ones look like. This is the we produced the TI64, the commercial grade, and of course we were able to produce our experimental alloys as well. And you can see just looking at both, after machining, you can really see the difference between the two of them. But of course, if you analyze the composition, you would see the difference. And of course, we try to look at the microstructure of the TI64 and that of the one of all of the experimental titanium alloys. But I'm showing the microstructure of this particular one where we retain 1 weight% of vanadium, and we replace the rest with 3 weight% of iron. And you can see that the microstructure they're similar because they both have lamellar morphology, basically. So it's a fully lamellar structure, comparing the as cast of TS64 with that of experimental titanium alloys. And if you go to the SAM, and you can at least you have higher resolution and you can see more, and you can see two distinct phases, which is the alpha phase and the beta phase. We were trying to see, although the result is not shown here, we did XRD analysis and we didn't find any TIFE phase in our alloy. Any of the intermetallic compounds were not in the experimental alloys, although we did find it in the Ti 6Al4Fe alloy, according to the SRD result that we have. But in terms of the partial substitution, what we had read in literature that vanadium, retaining a little bit of vanadium could suppress the formation of the TIFE intermetallic compound. We were able to establish that. And we were able to use EDS analysis to confirm which phase is alpha and which phase is beta. So alpha is the HCP hexagonal close pack structure, and the beta is more or less the BCC structure. The reason why we want the BCC structure is that it allows for easy processing of titanium alloys compared to the hexagonal close pack structure, and that's why you want the combination of both, so it gives you good strength and ductility at the same time. And we carried out compositional analyses, and we were able to, and this was done at Scroobies, and we were able to confirm that the amount of oxygen and nitrogen in the alloys was lower than the standard that you would have. So we were happy with that result, because if we had oxygen content more than 0.2% and nitrogen more than these values that we have here, 0.05%, that would be detrimental to the mechanical properties of the alloy. So we were able to keep the oxygen, nitrogen, carbon content below the standard requirement, so which is good. And we achieved this both in the commercial grade and of course the experimental alloys as well. So what does this mean in terms of mechanical properties? Remember, we started from 10 grams, we moved to 50 grams, and of course to about 5 kg. Just comparing the commercial grade with the experimental alloys, you can see the iron was even strengthening the alloys more. So you get more strength as you replace vanadium with iron. Due to what we call solid solution strengthening. And at least we're happy that what is causing the strengthening is not the oxygen and nitrogen, because that would have been a disaster. So, and we carried out this experiment on the 5 kg alloy. We were able to carry out tensile test, because now we have samples that are big enough to machine tensile samples, and we were able to gather the result that I'm showing you in this table. And I mean, at the CSIR lab is a SANA's approved laboratory. And we didn't end here. We sent the sample to Johns Hopkins University for nano-indentation results, just to validate what we've done at CSR. And you can see that in terms of the elastic modulus of both alloys, they're very, very close. This is the same samples we produced here, tested in South Africa and also analyzed in the US, and we got similar results. So we have confidence that the alloys are really good. And one thing that I want to also show here is that consistently you will see that when you have partial substitution of vanadium with iron, we have higher strength and higher ductility compared to when you have the standard alloy, which is Ti64. And we produce this alloys under similar conditions. So, which means that iron does not only improve strength, it also gives room for ductility. And of course, the reason for that is you have increased beta phase, the BCC phase, as you had iron, because iron is a beta stabilizer anyway. So, that takes care of the mechanical properties. Now, what have we learned so far? We were able to suppress the formation of TFFE by the idea of having that partial substitution of vanadium with iron rather than the full replacement that has been done previously. Again, we improved the strength slightly, and of course, we even have improved ductility. Then if you now look at how much cost you could save, and all these the alloys we have produced, we produce them from pure elemental powders. So we looked at the cost of each of these pure elemental powders, and we did cost analysis on the different alloys. We were able to save up to 7%. If you apply that to the ballpark figure, we have this reduction in the amount of in what we have this reduction basically, and this is what the implant will now cost if you have to sell it to a customer. Of course, when I get stock previously, someone will ask me, but that is not the manufacturing cost. But the manufacturing cost is not the main thing. It's the amount that the patients, the customers assess this implant that really matters. So I applied that cost reduction to how much they would get these alloys when they need them, or maybe the implant material when they need them. So that was a marginal reduction in cost anyway, but at least we made some progress. So I know I have spoken about, used some technical terms here, and you probably, maybe if you're not a metallurgist, it might be difficult to understand, but I have a user-friendly article which is published on Conversation Africa. You can just read, you can just check on the internet and read, and it simplifies everything. Okay, so now Prof was being critical, and is that the best you could get in terms of cost reduction? Just 7%. I said, well, if we play around the thermomechanical processing parameters, we could optimize it and reduce the cost further. Again, what did we do? So remember, if you produce titanium alloys, you're not going to use it in this form. You have to subject it to different secondary processing steps like forging, rolling, extrusion, machining to arrive at these components that we need. Okay, so like intermedullary nails, or maybe like the artificial hip and the plate and screw to fasten bones together so that they can heal quite quickly. And for you to move from this as cast or this billet or ingot and to these finished components, if you follow the classical procedures that is well reported in a foundational textbook, you will need several steps basically to be able to achieve this. I had shown you previously that the microstructure of the cast material was a fully lamellar structure. But for thermomechanical processing, for ease of processing, we always like a rounded structure or an aqueous microstructure. And for you to move from this A to B, you can use either of this pathway, the red path or the blue path. But if you count the number of steps, it's 1, 2, 3, 4, 1, 2, 3, 4. So could we find a way to reduce this to one single step and see whether it's possible to start having some rounded structure rather than having elongated structure or a lamellar structure? And that is what we did using our facility Glebo 3500 thermomechanical simulator. And again, I'm showing you the typical microstructure of as-cast Ti6Al1V3Fe alloy. This is an alloy where 4 weight percent vanadium has been partially substituted with 3 weight percent iron. And we explored, we looked at the range of temperatures and different deformation speed here. And we wanted to see, would we have conditions that are detrimental to processing of these alloys? Then would we have conditions that will start giving us rounded microstructure? And the rounded microstructure, in terms of technical term, it's called a globularized microstructure. So we came up with what is called a processing map, which was popularized by Prasad and co-workers around 2002. And after getting our stress strain data, we converted them to processing map. And the processing map just gives you an idea of what's happening, basically. So if you process the alloy at this temperature and this deformation speed, which is in terms of technical term in the hot deformation space, it's called the strain rate, you would have a situation whereby you are introducing unwanted defects into the material, and we could confirm this using microstructure. You see, and this is not a microstructure you would like to have in your structural material, even for bowel implant application. But if you move away from this region, still very low temperature but high deformation speed, you're not seeing those rounded structure that we like. But as you increase the temperature and reduce the deformation speed a bit, you can begin to have those rounded structure, which is the globularized microstructure. If you text TRC4, the gold standard and the most utilized titanium alloy that we have in the world, under similar conditions, you would have this behavior. So we were able to establish that yes, we can reduce those 4 steps by just exploring these parameters, deforming at temperatures around 900 and 950 and reducing the deformation speed to about 0.1 to 0.01 per second. But this is presented as a log of strain rate. That's why it's different. If you do the conversion, it's more or less 0.1 to 0.01 to 0.1 per second strain rate. Within those regions, you can begin to have those rounded structures, and that is really good for processing of titanium alloys into different shapes that you would like it to be. Yeah. So what did we learn in that case? We were able to establish unsafe processing window where you shouldn't ever try to deform these experimental titanium alloys. And we were also able to establish the sweet processing parameters that would allow you to go from lamellar structure, elongated structure, to the rounded structure. And this can then help to reduce the amount of steps that you need for processing those alloys. And if you apply the 30% cost reduction the 30% that thermomechanical processing contributes to the conversion of billet into different components. If you try to save that particular cost, then you will arrive at this ballpark figure, which is substantially lower than what we had when we just did alloying. And we've managed to convince experts within the scientific community with quite a number of publications that we have in this space. And apart from that, I would say that this is still not cheap for someone who is living in a village in Limpopo who's got a bone fracture and is not a medical aid. They can afford this. And that is the more reason why 5 years ago we started looking at making steel lighter by developing FeMnAl, chromium, FeMn, Al, Cr, and C alloys. And we've gotten some results in that area, but hopefully, if I have the opportunity to chat with this community again, I would like to show you some of the progress we've made in that space. Prof. Salim said, well, you managed to reduce the cost, basically, but we know that iron is highly susceptible to corrosion. Now, adding it to titanium, we do not degrade the corrosion behavior of this alloy. And this is an area where we really like the results that we have seen. Well, I have a response for Prof. Karim in that space as well. So we looked at different corrosion media or environments. We use basically electrochemical techniques, which is open circuit potential and linear polarization, to try to understand what effect is iron contributing in terms of corrosion performance. And we were able to see that if you just do OCP, and this is an alloy where you've totally removed the vanadium, and here you have partial replacement. In very strong reducing sulfuric acid, you can see we have corrosion products formed here, which is telling you like maybe it's a bad idea to add iron to to replace vanadium with iron. But if you do the partial substitution, you don't have this much corrosion products. And you can see the TSS for it does seem like nothing happened, basically. But this can be misleading because the open circuit potential does not tell you the entire story. You need to know at what rate will this material rust or dissolve when you expose them to this environment. Mind you, this is not a physiological environment. This is an acidic environment, but we wanted to test the strength of the alloys we've developed first. And if you look in terms of corrosion rate, you will see all the alloys that have partial substitution of vanadium with iron. In these two cases, they have lower corrosion rate compared to when you replace the vanadium entirely with iron. Okay, and the corrosion rate of the Ti6Al4Fe and that of the gold standard material seem to be similar. And you can see the result here as well in terms of the linear polarization curve. And we didn't end up here. We then look at 3.5 weight percent NSA, which is also too extreme when you compare to physiological solution. And here, of course, you expect titanium to be happy in this space, regardless of how much iron you had, whether you do partial or total replacement of vanadium with iron, the corrosion rates seem to be similar. And then that gave us the confidence to move forward and test in physiological solution. And we try to do all of this in glass. So it's not in vivo, it's not in human being. So we simulated diabetic and non-diabetic solution. And this was really inspired by, the fact that my father is diabetic, and I would like to see if he's got a broken hip and we have to do maybe give him an implant. We have to see if my alloys would be friendly in his body. And if you see in all situations, when you replace all the vanadium or you do partial substitution, the corrosion resistance of the alloys are more or less the same, and they are way lower, at least 100 times lower than what has been benchmarked as the maximum permissible corrosion rate for metallic implants. And this seemed to be a very, very positive result for us, knowing fully well that if you start having very high rate of corrosion, that could be detrimental to the human body. So, and again, from corrosion standpoint in physiological environment in glass, we were quite happy with the result that we got. So iron does not only improve maybe strength and ductility, especially when you have situation where the substitution is partial, it's not total, right? So iron also has a way of helping to slow down the corrosion in extremely acidic environment. But in terms of physiological solution, it's just happy. You can compare it with the Ti64. Now, we went back to the acidic solution. We wanted to see what is really happening to the oxide layer, because the way in which titanium resists corrosion is by reacting with oxygen to form titanium dioxide, and that protects the metal from or alloy from corroding or rusting. So when we looked, so we approached them at NEMISA, and they had to do X-ray photoelectron spectroscopy for us. And in the technique, I've shown the raw result without trying to replot replot it at all. And what we found is for when you all in cases where we have iron in the alloys, in all the iron containing alloys, the thickness of the titanium dioxide is actually higher than that of Ti64 that has 4% vanadium. And then this seemed to be counterintuitive, because we expect that, oh, maybe iron should accelerate the corrosion behavior of titanium alloys, but this is not what is happening. If you look at the first figure here, which is that of titanium Ti64, basically the gold standard material, after 60 seconds, using the sputtering technique on the XPS machine, what you would find is that after 60 to 65 seconds, you've already removed all the TiO2 layer, because here, this is the TiO2 layer, that's the oxide layer. But let's look at all the iron-containing alloys. In this case, we don't even have aluminum, and we didn't even have any vanadium. And you can see it took about 200 seconds for you to remove all the titanium oxide layer. And when you now go to our own alloys, the ones we really love, which has partial replacement of vanadium with iron, you would see that even after 220 seconds, we still have higher thickness of titanium oxide, because here again, the color coding is different, but I intentionally present the raw results without having to replot them. So you see that we have higher thickness of titanium oxide in that case, and we also here as well, we have the same situation happening. We could observe the same trend, and it does seem to me that maybe it's not a bad idea to add iron to titanium, because many of the opinion that maybe adding iron to titanium is never a good idea. If you do partial replacement, you stand a chance of improving corrosion and mechanical properties. But what we don't know is how is iron promoting the thickness of the titanium oxide. We don't know that, and this is one of the areas where we hope that we can find collaborators who can help us explain what is happening in that case. And the role of adding PGMs to titanium is well established. Molybdenum, tantalum, and niobium is well established in terms of corrosion performance and how the titanium oxide is formed. But when it comes to iron, even aluminium, there's still so much to learn in that space. The role of copper addition, the role of manganese addition, these are other alloying elements that have been explored in terms of corrosion and what happens in terms of the protective oxide layer. Those are not readily available in literature, and they are simple fundamental questions that I think that people can explore and learn about. So, but from what we have done so far, what did they learn by adding iron to titanium? We found out that you can actually improve the corrosion resistance. We found out that iron seems to be promoting the thickness of the the titanium oxide, and this explains why, in very extremely strong acidic environment, the iron-containing titanium alloys, especially when you have partial substitution, you have a situation where the corrosion rate is reduced substantially. Again, our conclusion would be partial substitution of vanadium with iron is beneficial for corrosion resistance. And we need more work to be done in that area so that we can settle the argument around, oh, iron is negative, iron has negative influence when you add it to titanium. It does not only reduce cost, it can give you improvement in mechanical properties and corrosion performance. We managed to convince experts within the scientific space by publishing some of our findings in all of these journals. So this is the last question I was asked. I would imagine Prof. Karim would ask me. Interesting corrosion results, and at least you're steering a debate on what role iron is playing in terms of corrosion of titanium alloys. But if you put these alloys in human body, did you do any cytotoxicity assessment? So that's a good question. Of course, we thought about it, but only recently, and that was last year when I asked one of my fourth year students to work with Dr. Essa and Professor Yaya Shinura to carry out cytotoxicity assessment of the alloys. I'm not an expert in this area, but I have shown the procedure where they have used, where they try to get extract from the alloys. It's more or less like you trying to corrode the alloys, and this extract, then you then expose it to fibroblast cells of rats. No, mice basically, and they were able to then study, the cell viability, what's happening. Of course, we have positive control for cytotoxicity and negative control for cytotoxicity, which I would show in the next slide. So in this case, they have used a particular reagent. In this case of B2, they've used a particular reagent to establish positive control for cytotoxicity. So all the cell had to die. Uh, and in this case, it's they didn't have the reagent that would allow the cells to die to die. So in this case, it's a negative control for cytotoxicity. But if you look at our alloy extract, you can see that not all the cells died, but we see that some of the cells. So the rounded shape of the cell shows that they are dead. They are not. The cells are dead, and in all of the cases here, you would see that we have a situation where some of the cells died and a majority of them are still healthy. So, so this is an image. These images are just showing what has happened in terms of positive control and negative control. And when you use the alloy extract, what you find is, are you finding situations that are consistent with positive control or situations that are consistent with negative control? So, and they were able to quantify the cells basically, and the quantification is represented in terms of cell viability. So there is 100% concentration of the extract, then they diluted it to 50% as well. If you look at the dilution, we should be closer to what you would experience in human body because, of course, the fluids are currently flowing; they are not stagnant. So you would see that both the experimental alloy, in fact, in this case, we also considered 316 stainless steel, which is the gold standard stainless steel material used for implants, and we have the TI64 as well. You would see TI64 as well. You would see that under dilute concentrations, we find the cytotoxicity performance of the alloy, it's really good, which means like we have less cytotoxicity. The cell viability was way ahead of way more than the 70% threshold that has been recommended as the minimum. But when you have 100% concentration of the extract from the alloys, you can see that the experimental alloy or the low-cost alloy that we have developed performed poorly against 316L and TI64. Okay, it's inferior to it, but the value still exists. The um, minimum threshold, which is 70%, that you would want to see in a bioimplant alloy. So, in terms of status, what we found basically in summary is that we were able to establish the 70% threshold stipulated in this ISO standard, but the performance seemed to be inferior to that of TI64, and we want to understand why. At that high concentration, we are having um, we are having some toxicity experience. But as soon as you dilute the system, uh, then you have a situation where the performance seems to be similar to the gold standard material, which is TI64. In all, considering the cost benefits and considering the performance that we've had in terms of corrosion and mechanical properties, and now some of the early data that we've obtained from the early data we've obtained from the cytotoxicity assessment, we think that yeah, we are heading somewhere in this, and we hope that with more work that we'll do in future, we'll be able to explain certain mechanisms and how find ways to improve the performance of these experimental titanium alloys. So these are some of the previous publications that I've shown you. And what are we considering next? The first thing that we would like to do, which I think is fundamental to, the development of iron-containing titanium alloys, is to understand how iron is promoting the thickness of TiO2 film from what we have gotten from the XPS analysis. And it will be good to extend this beyond iron, look at copper, look at manganese, nickel, because all of these has not been, are yet to be studied. Then we would like to do more work on cytotoxicity assessment because we are really at the early stage. And we would like to also explore antibacterial properties. But of course, if some of the work that Prof. Cornish explore or look at is to improve antibacterial properties of implants, and that sometimes involve adding copper to the alloy composition. And what role is copper playing in terms of the TiO2 film that is forming, and of course, how would that then mitigate bacterial growth? These are some of the questions that so we would also like to answer. We don't have copper in our system, but do we have any antibacterial property for any reason? I would be surprised to see that. Anyway, but at first we need to improve the cytotoxicity, reduce the cytotoxicity, and that we have at 100% concentration. Again, we continue to explore the low density stainless steel. If given another opportunity, I'm happy to share some of the results that we've had in that space. And it seemed really to be the promising pathway to actually reducing the cost of bowel implants, so that by 2050, older adults or geriatric populations in general will probably consider low density stainless steel as the implant of choice rather than titanium, except if we find new ways to reduce the cost of extracting titanium from its ore. The crow process was invented around the 1940s. It's high time we find alternative processes cheaper. At least we know how to optimize the thermomechanical processing. We know how to play around the alloy chemistry or alloy composition. But to really reduce the cost of titanium, we need to find ways to extract pure titanium from its ore and these ways have to be cheaper and more efficient. If you're able to do that, then titanium may stand a chance. Otherwise, I do believe that low density stainless steel seems to be the future. Um, and I would like to part with this. This is one of my mentors. Of course, I've never met him, but I looked him up after he passed away. I wanted to find out what was his last message to the world, and I was able to find this. And he said, Steve Hawkins said, "Let us fight for every woman and every man to have the opportunity to live healthy, secure lives full of opportunity and love." And said, "We are all time travelers journeying together in the future, but let us work together to make that future a place we want to visit." Okay, the question that I want to ask is, how do we then visit the future? For me, I think the way to visit the future is to solve the problems that we can see would definitely happen in the future. So if we would have older adults in 2050 and most of them will live in developing countries, and these developing countries are low and middle income countries, and we know these older adults will experience hip fractures and other bone diseases, and they would need implants. I think it's high time we start working on reducing the cost of implants. It's not only implant, all other medical interventions, we really need to reduce the cost so that we can make life easier by 2050. I'm not sure if I'll still be around by then, but if I would be around, I might be some of the beneficiary of the work that I've done. On this note, I want to say thank you, and I'm happy to take your questions.
Thank you very much, Professor Bodunrin, for an interesting and enlightening talk. There were two things I really liked about it. One is the way it was hooked on helping people. I think that's really nice. And the other way, I like the way you did it by having Professor Karim asking you questions, because he can be a very formidable person. So I thought that was lovely. Before I throw this open for other people, I just got a comment. The Kroll process, no, the reason why the South African titanium sort of project that was running at CSIR mainly and Mintech a little bit, they were working together on it. The reason why that sort of fell over was they couldn't get it to work in large stages. So the whole thing fell apart because the whole process was sort of centered around the idea that they would make something, they would develop this process which would replace the Kroll process, would be much more efficient, and therefore cheaper, and therefore there would be lots of titanium available for many, many projects and many, many ideas. And then when it didn't work on the scale up, I'm not supposed to say too much about this, but everything else that was hanging off it fell apart. So that was why it disappeared. And you also mentioned 3CR12, which was an excellent stainless steel. And that was the result of much funding from the government to places like CSR mainly. Mintech were also working on that, and and to the universities. So there was a whole generation of metallurgists who came through on that. I wasn't part of that, but I saw the last stages of that when I first came out to South Africa. And the moral of that is that if you've got more funding to throw at something, you've got more chance of getting something
Mm.
out at the end. Right, so that's my comments, but well
Okay.
done on an excellent presentation. I'd just like to ask a couple of questions.
Okay.
Have you ever thought, what about the reported deleterious effects of aluminium and vanadium? You probably knew I was going to answer that.
Yes, yes, yes. Okay. Well, we definitely the reports on the effects of vanadium on the negative effects of vanadium on human health. But if you look at the currently TI6AL 4V is the gold standard material. It's still being used. Despite the reports of having vanadium as a very dangerous annoying element to have in TI64. But our own composition has just one weight percent of vanadium. That's a little is all you need. So if we're not able, that effect will still be there, but in terms of the amount of vanadium that you would then release into the body because we've reduced the weight fraction substantially, then I think that we would have maybe a much more friendlier material in our alloy system compared to the gold standard TR64. That's my comment on vanadium. In terms of aluminium, yeah, so yeah, there are quite a lot of articles being published in that space as well, but there's still no clear evidence on how aluminium then crosses the blood-brain barrier, given that aluminium is mostly associated with Alzheimer's disease. So there's still a lot of work to be done in that area, and that's why in our system we still favored aluminium a bit. But the most promising alloy composition that we've worked on was the one that has 4.5 weight percent aluminium. When we carried out wear testing, tribal corrosion testing, the alloy composition with reduced amount of aluminium seemed to perform better globally compared to the one with 6 weight percent aluminium. So in a way, these dangerous elements, we're trying to reduce them in our system, but we don't want to take them away totally because they also have other effects. For example, in the case of vanadium, just 1 weight percent can suppress the formation of TIFE. And in terms of the aluminium, we were able to reduce it to 4.5. That has positive effect on thermomechanical processing, which I didn't mention previously. But again, like I said, it's been really associated with Alzheimer's disease. But I've read a bit in that space. There's still no substantial evidence on how aluminum would cross the blood-brain barrier. Of course, the aluminum will get released into the bloodstream first, and then how does it then get into the brain? And then facilitate, Alzheimer's disease. So that is still not clear, but of course, what we've done basically is to reduce the amount of aluminium. There are other alloy compositions where you don't have to maybe use aluminium at all. We can use zirconium to replace aluminium, but again, we need to check, is zirconium also safe in the human body? There's still a lot of work to be done, and we both work in this area, and we can begin to look at really the future. But as of now, the most utilized material is still TR64, and it contains this aluminum and vanadium. In our systems or alloys, we have tried to reduce vanadium. We've also tried to reduce aluminum, and we believe that will be less detrimental to human body compared to the gold standard material. Thank you. And sorry for the long-winded response.
Oh, that's perfect. Thank you very much. I have been looking through to see if there's any other questions. If you've got a question, please ask. If not, I'll ask another one. But I don't want to hog our speaker.
Yeah.
You talked about making shape, and you probably, I'm sure you know about this, but might be useful to our audience. Have you considered 3D printing or additive manufacturing as a way of making a shape? Thanks.
Yeah, thank you so much, Prof. When I presented this talk in Switzerland during the Arcanex competition, the same question was asked. In fact, 3D printing gives us the opportunity to even make components cheaper. Because now there's less machining, and we don't have, of course, we didn't have to go through all these multiple stages of thermomechanical processing. But the question then is, what sort of microstructure would evolve from the 3D printing? Because it's relatively new, and we're still learning that. We're still trying to find out more information in that area. I've not done any work on 3D printing of titanium alloys, but I know that it's an alternative pathway to making biomedical components. And I think that it might solve some of the challenges that we have in terms of thermomechanical processing, especially maybe machining, because machining leads to a lot of waste when you are producing titanium-based components. So with 3D printing, you get rid of that substantially, and you can save some costs. So it's a promising processing route, but not enough is known, given that there are so many parameters that you also need to optimize in that space to get components that are fit for service, or that would give you the kind of performance that you need. I would like to make one last comment about 3D printing. When you print small components, maybe you have a little bit of more control, but when you start printing larger components, first, the process would take a long time. Then the thermal gradient that you would have, because of the layer by layer approach that is used in 3D printing, then you then begin to have heterogeneous microstructure. And people are considering maybe what they should do is then subject some of these 3D printed components to thermomechanical processing to try and even up the microstructure. I remember towards the end of my PhD, a new technique evolved. Was developed in the UK, which is fast forge. In this case, it's not 3D printing; it's more or less like combining spark plasma sintering with a forging process, and you make a rod. You get a component that has similar microstructure to what you would have when you do rod processing. It's a very promising technique, but again, you have limitation of size. If you have to make artificial hip, that's a little bit the geometry is quite interesting first. The second thing is like it's large enough to introduce a lot of defects that we see in 3D printed components these days because of the large thermal gradients that you have there. But it's a promising technique which we can optimize the different parameters, and maybe in future we'll be closer to what we obtain from the conventional process of casting and forging. That would be my response. And sorry again for the long-winded answer. There's no yes or no response to that. Thank you.
Thank you very much for that. It would be
Yeah.
boring asking questions with a yes or no answer in this
Mhm.
environment.
Yeah.
One of the nice things about 3D printing is that currently, I don't know how long, um, I don't, I don't know how long this will last, but currently there is funding in South Africa which which allows for research um, in 3D printing. And that's something that you might think about in the future.
And
Um, I think
okay.
I think we can talk to it about it offline.
Okay.
And yeah, has any? I can't see any questions from anyone else, and I don't want to hog the speaker. Um,
It's either I've managed to discourage them or
well, there's one of our colleagues there, so I'm surprised he hasn't asked something. Um,
Mm.
so yeah, so I don't want to hog the speaker. So if there are no other questions, I'd really like to thank our speaker again. It was a very interesting talk. I thoroughly enjoyed it. I learned some more stuff, and I love the way you presented it, and I found it
Thank you,
very
sir.
interesting. So
Thank you.
thank you very, very much.
Thank you.
And I think you hinted that you would be available to talk again, so we
Yes.
might ask you to talk again.
Yes. Yes, I would really love to share some of the findings that we have on the low density approach, especially now that we are managing to convince the scientific community. Because previously they didn't like the idea and most of our papers got rejected, but now um, they're getting friendlier with us, and it would be nice to share some of our recent findings in that area with the Rare Society community. And thanks so much for having me. I would like to make one comment around the funding available for 3D printing. I think that's the right thing to do. I think everywhere else in the world now, there's a lot of funding going towards 3D printing. So, and it's something that we should really consider because the compositions that that we've produced using conventional processes, we need to see if we could 3D print them and how would they be different from the composition from what we've gotten using conventional processes. And thank you so much for having me once again.
Oh, thank you. Thank you very much.
Yeah,
I'll talk to you soon.
thank
Thanks a
you.
lot. And
Yeah,
thanks
thanks.
everybody for being here. And I hope you enjoyed it as well. So we'll have another um, talk next month. Thanks a lot.
Yes.
Goodbye.
Goodbye.